Okay, so let's take a look at the solution to this problem. We're going to calculate the change in kinetic energy and the change in potential energy of this falling bag of, God only knows why I chose tortilla chips. I'm not really sure if I was hungry, but we have a bag of tortilla chips which are falling. Okay, so let's pull up the solutions here. These are just the lecture notes that you should be able to find on Blackboard. And so if we look at the solution, we'll find that, I've gone through the 4 steps. We have the known, we have the find, we have the schematic and given, and here's our analysis section. So let's just briefly review the known, right? We know that we have a 1 kilogram bag of tortilla chips. We have a change in height of 10 meters. So it's decreasing from 20 meters down to 10 meters. We have an initial velocity of 15 meters per second, and the velocity increases as the bag falls to 30 meters per second. We're looking to find the change in kinetic energy. Remember that delta means change in kinetic energy, and the delta here is change in potential energy. So we're going from remember, the change in kinetic and change in potential are the final state minus the initial state. Schematic and given, so this is very similar to the drawing in the slides. We have a bag that's falling from an initial height to a final height, and the velocity is increasing. So if we were to look at the analysis, it's not too tricky here. We have a change in kinetic energy. We use our equation from the previous slide that we have 1/2 times the mass times the final velocity squared minus the initial velocity squared. So 1/2 times 1 kilogram. Then we have 30 meters per second squared minus 15 meters per second squared. One thing we should take a look at is we have to take a look at the units here, right? So we end up with, if we do the calculation, we get 337.5. And if we look at our units, we get kilograms times meters squared per second squared. If you remember, a newton is a kilogram meter per second squared, right? And this is incorrect. Yeah, so a kilogram meter per second squared, and here you can see that we have kilogram meters squared per second squared. So sorry, I miswrote this. This should be Newton times meter, force times distance, not Newton divided by meter. My apologies on that. So what we've done is we've taken a Newton, a kilogram meter per second squared, we've multiplied it by a meter, and we end up getting a joule. So yeah, please disregard the Newton divided by meter. It's Newton multiplied by meter. So we get 337.5 joules, and here we have a potential energy, mass times gravity times change in height. So we have 1 kilogram times 9.81, and our change in height is 10 meters minus 20 meters. So we end up with a change in potential energy of negative 98.1. And so again, kilogram meter squared per second squared is equal to a joule. And so, this is actually just an example where numbers were sort of pulled at random. But if we were to do an energy balance calculation, the change in kinetic energy should be similar to the change in potential energy. The magnitude should be similar. So in fact, these numbers were just sort of made up. But in a more real-world example, these values should be very close unless there were, some other forces being applied to the object. Okay, so there's the solution to example 2.1. Let's go back to our lecture slides here. So, as I just mentioned, when we look at, excuse me, I went one too far. And when we look at our energy balance equation, which is derived from our conservation of energy, we would have potential energy being sort of equal and opposite to kinetic energy, assuming there's no other forms of energy being applied to the object. So let's briefly define conservation of energy. It's the total work of all the forces acting on an object equals the sum of the kinetic energy and the potential energy. Increase in height and or velocity transfers energy to the object. So you can imagine if you increase the height of an object, you've increased its potential energy. If you increase the velocity of an object, you've increased its kinetic energy. So if we assume that only gravity is acting on an object and there are no other outside forces, we can say that the change in kinetic energy plus the change in potential energy is equal to 0. And if we move one, we can move one portion of the equation to the other side, or in this case you can see I have my final state, so velocity at state 2, height at state 2, and then on this side I have my velocity at state 1 and height at state 1. So essentially we've set equal the final state is equal to the initial state, the potential and kinetic energy for each state. An example of a falling object would be, you can imagine the object is going from a height that is higher to a height that is lower, so we would have a decrease in potential energy, right, because the height is decreasing. As it's falling, the velocity would increase, so that would give us an increase in kinetic energy. If we were to, let's say, apply a force to an object maybe, or if we threw a ball up in the air and let momentum, carry the ball to a certain height, we would have an increase in potential energy because the height would be increasing, and we'd have a decrease in kinetic energy because as the ball went up, the velocity would decrease due to the force acting on it from gravity, right? Okay, so let's get into a more thermodynamic definition of work. So work is in units of kilojoules a lot of times. It could be in units of joules. But yeah, work is done by a system on its surroundings and can be equated to the raising of a weight. So if you remember, we had an equation where we had work is equal to force times distance. So from some initial height to a final height. In a thermodynamic perspective, we're going to think of it as a displacement from initial state to a final state. And you'll see shortly we're going to relate this to pressure and volume as well. So work is not a property and therefore has no meaning at a given state. It is a process between two states. So it occurs from one state to another. You can imagine when you do work on a system, then you are changing its state from one state to another. So it's actually a process. A really important thing to remember in this course, that's why it's highlighted and flashing there, is that the sign convention for work. So commit this to memory, read over it over and over again, just memorize this portion. So a positive work is equal to the work done by the system on the surroundings. So this is work done by the system. Negative work is work done by the surroundings on the system. Or you could think of it as just work being done on the system. So positive is work done by the system. Negative is work done on the system. So here's an example where we have, we could just say, let's just say this is a cylinder and this is a piston. Maybe this has a circular cross section and there's, we'll just say air is in here. Well, if the air, and maybe we'll assume that the air is being heated up or something like that, and the air is expanding. It's forcing this piston outward. Now, would that be work being done on the system or work being done by the system? Yeah, so you should have said work being done by the system, right? Because you can see we have our boundary drawn here. Our system is defined within the boundary, so that's our gas. And that means if the piston is being forced outward by the system itself is doing the work on the piston. It's forcing the piston outward. So in this case, it's actually displacing the piston, it's forcing it outward, and it's increasing the volume within this space. So if, let's say we heated this up, we might be increasing the pressure in here, and that pressure would be forcing that piston outward. So this is work done by the system on the surroundings. And then on the flip side, maybe we apply a force to the outside, to the piston, and we compress this gas, right? So in that case, we are applying a force, we're doing work on the system, we're compressing this or decreasing its volume, and so that's work done by the surroundings on the system. So it's work done on the system. In this case, maybe we have some sort of a force being applied to the piston. Okay, so as we mentioned before, there's a difference between work and power, right? And I think we've talked about this in some previous lectures, but power is equal to W dot, right? And that dot means it's a rate of change. So it's the rate of energy transfer by work. So in this case, W dot is equal to energy over time. So it could be kilojoules per second. It also could be joules per second. But kilojoules per second come out to be kilowatts. And so kilowatts, we can also do the calculation. W dot is equal to, instead of force times distance like we did with W, the minute we put the dot, we now are dividing it by time. So if we take distance divided by time, we get velocity, right? So it's force times velocity would give us a work rate. And we'll talk about some other ways to calculate power in future lectures. Work can be calculated by integrating power with respect to time. So if we were to have, if we were to know the work rate, let's say, and maybe the work rate is constant over a certain period of time or something like that, maybe we have a calculation, an equation for the work rate and how it varies over some T1 to T2, we can integrate that and we can end up with the amount of work that occurs over that period of time. Same with, maybe we know what maybe the force varies over some time from T1 to T2, or maybe the velocity varies. If we're given those equations, we can integrate those with respect to time, and we end up getting force times distance, which would give us work. Okay, so here's an example problem, sort of a simple example problem looking at force and how that can be applied to the power, in this case the power necessary to overcome drag forces due to air. So here you can see this very detailed drawing of Lance Armstrong, and we're asked to find what the necessary power of Lance Armstrong is to overcome the drag force when riding his bike at a velocity of 32 kilometers per hour. The drag coefficient is 0.88. The frontal area of Lance is 0.36 meters squared. That area is basically the area that is blocking the, let's say, blocking the air or blocking the wind that is being applied to him and causing that drag force. The air density is 1.2 kilograms per meter cubed, and the drag force is equal to 1/2 times the coefficient of drag times the area, I guess the frontal area of Lance, times the density times the velocity squared. So again, I suggest that you take out a piece of paper and a pencil, see if you can figure out the power given the information from this example problem, and in the next video we'll go through the solution.